Hey, good evening, afternoon, morning, whatever it is for you guys when you watch this thing. Right now, it's evening for me. Seem to be getting these later and later and later. Um, Guys did pretty good on your PIOT quiz or test, whatever you want to call it. I looked at it and looked through a lot of you guys' stuff. I hope to have those graded fairly soon. And then I'll get those chapter 8 things up too. And we're still discussing some things of what I might allow you guys to do for your log test and or your rational test if you guys decide on that the outcome was not as you wished. I'm trying to discuss with some, we're not trying, we're discussing with the other two teachers on what would be fair and what would be a good representation for you guys to be able to do. So just don't worry about those right now. Just concentrate on this lesson. Focus in on right here. I got everybody to take that quiz when you were supposed to, so I really, really appreciate it. There was one issue, and the student contacted me as soon as they did. The internet went out with the weather going on, and so that's just fine with me. You guys communicate and just keep in contact, and we'll get through this. Okay. So we're going to start. It's chapter 7 out of our book. I don't know what we're going to call it, but I'm just going to go with these lessons, the 7-1. I think we'll do 7-2, 7-3. I don't know how hard we get into this, but this is something that is a little bit different than what you guys have been used to doing. It's not really algebra per se. I mean, it is, but it's not functions. I shouldn't say that because it kind of is functions, but it's not the continuous functions. How about that? It's not continuous functions like we've been dealing with. We'll talk about that when we get into this lesson here. You can see by the title here, define and use of sequences and series. And so sequence is just what you might think it would be. It would be a sequence. It's sequential. And then a series is like a sequence, except the series, we're just going to add it up. And so that's our plan for this chapter right now. A lot of you guys, I think, are going to like this. And there's going to be some of you guys that might get a little frustrated with this. You'll see me struggle with some of these. Some of these trying to figure out the actual formula, if you will, or the equation for the series. Some of them are a little difficult. You'll start seeing some patterns, and as we work through these more and more, you'll start becoming a little bit more comfortable with them. Just think back to quadratics when you first started seeing those and all the different ways. They became a little confusing, but you became more comfortable with them. Just like a rational expression. You just become more comfortable with these the more and more you do. So 7.1, sequence and series. Before we identified and wrote functions. Picture this like, again, chapter 7. Now we're going to recognize and write rules for numbered patterns. So a pattern, so a sequence or a series, okay? Key concept. So this right here, here's our key concept. And I'm going to be going back and forth between my notebook and the score here, but hopefully you guys can follow along. Hopefully I won't go too slow. Hopefully I won't go too fast. But the key thing is you guys is you can fast forward or rewind or whatever you need to do in order. Sorry about that. That just came on. In order for us to in order for you to gather. Okay, sequence. That's our first terminology. Is a function whose domain is a set of consecutive integers. If a domain is not specified, it's understood that the domain starts with 1. And so again, kind of get into the terminology here. They do use the word function. They do use the word domain. The domain are our input values. Input, output are our ranges. So we're going to input the domain of values. Typically, that domain will start with 1. We input a 1, and then we're going to output some value. So the value and the range are called terms. So instead of calling it the range, we're going to call it the term, the values in the range. So here's the first input value, the first term, and it's going to output some value. They put a sub 1, a sub 2, a sub 3, so far and so forth. Of course, these are going to be values for you. These are variables. A finite series has a limited number of terms. So in other words, you can see where it ends. 1, 2, 3, 4, 5. That's a finite. Okay. An infinite sequence would be one that just goes on forever. It goes on to infinity. So 2, 4, 6, 8, ... It's just going to continue on, continue on. Our number system are infinite. We're used to going on forever. A finite sequence will stop. A sequence can be specified by an equation or a rule. I'll use either one of those terminologies. I kind of like a rule better than I do equation. What rule do we need in order to get this value, or what equation do we need to? So I'm going to input a 1 and I'm going to output some value. So when I input 1 into my equation, I better get this. When I input 2 into the equation, I better get this. When I input 3 into the rule, I better get this. Okay? So here we go. Example number 1. Write the first 6 terms. And I can't cover this up like I do in class, but I'm just going to go ahead and write it down. A sub n equals 2n plus 5. And then we got another one. It's b, and I'll write it down, okay? F sub n equals negative 3 to the n minus 1. And they want the first 6 terms, okay? The first 6 terms. So you can see they wrote this, they've written this, they've written this, they wrote this 2 different ways. No, I'm not English, I'm math. This is a sub n equals, so this one's kind of like a rule. This one's more of an equation because it says f sub n. We like to write it like this more often, or at least I do. I write it more like this than I do this over here. I kind of get away from functions on this. I just treat sequences a little bit different than functions. However, you need to kind of associate the 2 together. So it's simply, we're going to write the first 6 terms. So we're going to write 1, 2, 3, 4, 5, 6. And if you want to, these are my terms. Okay? These are my terms. And so when I input a 1, what do I get output? So these are my domain values. These are my input values. I'm going to input a 1. So if I want to right here, a sub 1, that would be the first term, equals 2n. So it is 2 times 1. 2 times 1 is 2 plus 5, 7. So that's the first term. The second term, put a 2 right here. Again, don't worry about that. That's a sub 2. So that's telling me anytime you see this, guys, a sub 4, what is that? That's asking me for the 4th term. That's what it means. That's what the sub means. So a sub 4 is the 4th term. And that's why I like that better than this. Because if I do f of 4, that leads it more to be like a function as opposed to a sequence or a series. I'll talk a little bit about that in a second. All right, here we go. 2. 2 times 2 is 4. 4 plus 5 is 9. 3. 3 times 2 is 6. Plus 5 is 11. And now you can kind of start seeing a pattern here, and I'm covering a lot of that up. I apologize for that. 7 plus 2. So we're just adding 2 every time. 13, 15, and then 17. And if you want to make sure, plug in 6. 6 times 2 is 12. 12 plus 5 is 17. Okay? So that's the first 6 terms. Again, I like the a sub n a little bit better. We'll talk about it. Here we go. Here's the second one. So if again, 1, 2, 3, 4, 5, 6. And we're just going to plug and chug. That's it. So 1 minus, that's a negative sign here. That looks like multiplication. 1 minus 1 is 0. So negative 3 to the 0 power is 1. Anything to the 0 power is 1. Don't forget. 2 minus 1 is 1. Negative 3 to the 1 is negative 3. 3 minus 2 is 3 minus 1 is 2. Negative 3 squared is negative 3 times negative 3, which is 9. 4 minus 1 is 3. Negative 3 to the 3rd is negative 27. So something a little bit interesting here is going positive, negative, positive, negative, positive. So this one would be negative 2. You can kind of see how this is happening. 5 minus 1 is 4. Negative 3 to the 4th is negative 3, negative 3, negative 3, negative 3, negative 3, negative 3, 9, negative 3, negative 3, 9, 9, 9, 81. And then I just got to multiply that by 3 more again because it's going to be negative 3 to the 5th. This was negative 3 to the 4th. 243. All right? That should be fairly simple. We hope you get 1,000 of those. Just find the first 6 terms. Just plug and chug and go to town. Okay? So there we go with that. All right, draw me a little line across here. That was example number 1. guided practice. So here's write the first 6 terms of these. I'm not going to do that for you guys. This is pretty simple here. You guys are pre-AP students. This is when it starts getting a little bit harder. Write the rules for the sequence. So now they're going to give you the sequence, and let me try to cover that up there. They're going to give you the sequence. You guys can see it down here, and you guys now have to come up with a rule. So let me write this down. This is example number 2. Example number 2, and A is -1. -8, -27, and -64. Okay, I'm going to go ahead and do B at the same time. That way I don't have to come back and forth. 0, 2, 6, 12, ... All right, now I've got those written out. So these are infinite series. Okay, infinite, because they're going ... They're going on forever. These must have been finite, or they're finite to the first 6 terms. They could have gone on further. I don't really know. So our job is to write a rule. So here's what I like to do with these now, guys. And again, some of you will see these quick. Some of you will not. Some of these are difficult to find. Some of them are not. There kind of is a way to start seeing these, but there's kind of not. So this is the way I start to take this off with. Okay, 1. First term is -1. Second term is -8. Third term is -27. The fourth term is -64. And so hopefully I can figure out what the formula or the rule, if you want to, is going to be with just those 4 terms, because that's all he gave me. Now, sometimes you can take that out further. You can figure that out. But your job is to figure out, when I plug in a 1, what I have to do to get this. So, well, I can multiply 1 times -1. That works. Well, if I multiply 2 times -1, I don't get this. So that can't be the rule. Just go back up here to this one. What do I have to do to 1 to get 7? What do I have to do 2 to get 9? What do I have to do 3 to get 11? Okay. Well, 1 to get 7, I could do this rule right here, and that would give it to me. 2 gave it to me. 3 gave it. So whatever I plug these values in my rule, I better get this outside. Okay. All right. So 1 to get -1. Let's see here. 2 to get 8, and 3 to get 27, 4 to get 64. Boy, this is going to be hard to see, but you have to kind of start looking. 1 to 1, 2 to 8, 3 to 27, 4 to 64. Let me give you one other hint that sometimes will help you. Plot those points. So if I plot those points, 1, -1, 2, -8, 3. So this thing's shooting down really, really quick. It looks exponential. And look at what we can do, right? I can cube this value here and get this. I can't cube this and get this. I got to cube this and multiply it by -1 to get this. Cube 2 to get 8, cube 3 to get 27, cube 4. So I know that here I sub n equals, I know I've got to do this, but now it's not going to give me the negatives. This is going to give me the positives. So if you want to, just throw a negative sign right there. That's fine. If you want to put it in parentheses, put it in parentheses. There is more than one rule that will get these sometimes. Okay? More than one. So this is the rule to get this equation right here. Just again, check it just to make sure. If I plug in 4 cubed or -4 cubed. Either way, I'm going to get -64, and that works. Is that tough to see? It's not easy, but you just have to start seeing these things, okay? All right, letter B. First term, second term, third term, fourth term. Typically, that's what they'll give you is 4 terms. 0, 2, 6, 12. Okay? Now, what do I got to do to 1 to get a 0? Well, I can subtract 1. So a lot of times this doesn't help us. Okay, what do I got to do to get 2? Well, now, if I do 2 minus 1, I'm not going to get 2. So I can do 2 times 1. Okay, let's see. Hold on. Oh, let's see. So I could do 2 times 1. I could do 2 plus 0. So 1 plus 0. 2 times 1. 3 to get 6. Well, I can't multiply that times 2, but I can multiply that times 2. And I can multiply this, y'all see this, times 3. So this one, if I multiply, let's see, times 1, times 0, times 1, times 2, times 3. Well, that's kind of tough to see, but after a while, you kind of start seeing these things. Again, you just kind of start seeing patterns. Graph the points too. Again, if that helps you, look at points. 1, 0, 2, 2, 3, 6, 4, 12, and you'll start seeing that's somewhat linear, I think. Okay, so that can help me a little bit there too also. Here we go. A sub n equals. What I want to do, again, there's a couple different ways to do this. I'm going to take n, which is the 1 and the 2 and the 3 and the 4, and I want to multiply that times 1 less than what it was. This one wouldn't be linear. This would be exponential also. This would be quadratic. Let's look at it. 1 minus 1 is 0. 1 times 0 is 0. 2 minus 1 is 1. 2 times 1 is 2. 3 minus 1 is 2. 3 times 2 is 6. 4 minus 1 is 3. 3 times 4 is 12. That works. Now, some of you may have seen this. N squared minus n, which of course, if you distribute that, you will get this rule. So either one of those is fine. It'd be a little bit harder to come up with this rule than this rule. But there'll be some students that can do that. I don't care which way you write that. All right. So this part right here, this example is pretty tough to do. Okay. Again, you will start seeing some patterns on how to do this. Okay. You'll start seeing some patterns on how to do this. And then I'll start giving you some hints too, but I like seeing you guys get through these, the first couple. Here they talk about it right here, okay? And here's the examples, okay? Multi-step problem. I don't want to pull up the solution yet. Example 3. You work in a grocery store. You're stacking apples in the shape of a square pyramid. It has 7 layers. 1, 2, 3, 4, 5, 6, 7. Kind of hard to see that picture. In fact, let's go. There we go. Get me out of the way. Write a rule for the number of apples in each layer, then graph the sequence. Now, again, I'm not so worried about the graphing that. So the first layer, they're showing me that right there. Here we go. First layer just has 1. So the first layer has 1. The second layer, if you got to kind of picture this, I think has 4. 1, 2, 3, 4. Okay, because they're lined up in a square. So picture that, right? You got 4 apples. Oh, I'm drawing that. I'm writing it on my paper. You can't see it. The next one, it'll go 3 by 3 by 3. So that it's going to have 9 in there. The next one's going to go 4 by 4 by 4. That's going to be 16. You ought to start seeing a dang pattern with this. Let me go over here real quick and give you the paper here, right? Picture, right? Here's the 1 apple. And then the next one, this is the top view. The next one, you see that? So that's the top view if I'm looking down onto them. All right. Anyway, there's my sequence and there's my series that I'm looking for. Hopefully this one's pretty easy to see, right? 1 squared, 2 squared, 3 squared, 4 squared. That one's pretty easy. A sub n is equal to n squared. That one's a pretty easy one to see. You ought to be okay with that one. It says then graph it. Well, I mean, you've graphed this. We just got through graphing that. I'm not going to graph it. Here's that, here's that, here's that. Oh, I need to talk about the graph. Let's talk about it, okay? Here's what's interesting about that graph, right? Here, in this graph, if I was asked to graph this, okay? 1, 1, 2, 4, 3, 9, 4, 16. Do not connect these. Do not. There is no value between 1 and 2. There's not a 1.5 apple. There's not a 1 3/4 apple. There's either 1 apple or there's 2 apples. or there's 3 apples. So this graph will be a set of points. It will not be an exponential. It will not be a curve. It will not be, listen to what I'm saying, continuous. It won't be continuous. It's going to be just points. Okay? That's a big deal about this. These are sequential. They are points. They are not continuous. So don't connect these things when they tell you to graph them. It should just be a plot of points. Okay? Almost like a scatter plot, maybe? Is that maybe if that rings a bell to you or something? More like a scatter plot. Scatter plots, you shouldn't connect those points either. I know it's been a while since you guys have seen scatter plots. Move me over here. Doesn't look like there's a whole lot going on over there. Describe the pattern, write the next term. So here's the pattern here. Describe on the next term. Let's go ahead and just do that one real quick, just to kind of show you. That's the pattern. 3, 8, 15, 24. Describe the pattern, write the next term, graph the first 5 terms, write a rule. Again, your graph, when the instructions tell you to graph, don't graph it. We've graphed enough in here. I'm not concerned with graphing. Now, if you're trying to write a rule and you can't figure one out, it might help to plot those points to see if it's exponential, see if it's linear. Those type of things sometimes will help you. So let's go over my paper here. We're down here. Here's my point. So the first term is a 3. My second term is an 8. Third term is 15. Fourth term is 24. All right. And again, some of you may see it pretty easily. Some of you may not. Some of these are difficult to see. They really, really are. I know I'm going to do a sub n equals. And right now we got, I won't say half the problem, but you got a lot of the problem right now. This is, it's going to be a sequence in our series. We're going to do a sub n. Again, I like that better than a function. That's why I don't want to do a function, because a function tells me that it's continuous to me. That just says the word continuous to me. And so you could connect these things like I did right here. This is telling me it's a series, and therefore there's no points in between them. These are discrete values is what we call them in stats. Discrete, not continuous values. Okay? You can ask your stat buddies that. What do I have to do to 1 to get a 3? Well, I can add 2. Add 2. I could multiply it by 3. What do I have to do to 2? Well, I can add 6. Well, I can add 3 here, add 6 here. This would add 12. Add 3, add 6, add 12, add 20. I don't know. Multiply by 3. Multiply by 4. Multiply by 5. Multiply by 6. Times 3, times 4, times 5, times 6. I'm starting to see a pattern here. I'm going to take the n value, which is the 1 and the 2 and the 3 and the 4, and I'm going to multiply that by n. Now, n is 1, so I need that to be a 3. Can I add 2 to that? Four, 6, 4, 6, 3, 5, 2, 4, 1, 3. That works. That works. Now, did I get lucky? Did I know this? No, you just have to kind of start seeing these things. Okay? They want me to write the next term. So the next term is going to be the 5th term, and I need to multiply the 5th term times, let's see, 3, 4, 5, 6. So I need to multiply it by 7 to get 35. Let's see if that worked. 5 plus 2 is 7. 7 times 5 is 35. And again, if you want to, you can distribute that in. I don't care if you do or not. You might as well not. I think it's probably a little bit better if you don't. But let's see what the book did there. Oh, I don't have the answer to that. Nope. Okay. All right. Let me turn the page over. Kind of halfway through this lesson. To me, that the second example, or what I just went over, probably is the hardest thing. Trying to find those things out. Series and summation notation. Get back over here. All right. Series and summation notation. Do I need to center me up better now? There, that's better a little bit. Summation notation. So the term sequence added together. So sometimes we'll take these sequences or the series, if you will, so sequence, let's go back real quick. This is a sequence. Okay, 2, 4, 6, 8. A series is when you add the sequence. So instead of going 2, 4, 6, 8, 2 plus 4 plus 6 plus 8. All right? This is a finite and infinite series. 2 plus 4 plus 6 plus 8 plus ... This one's easy because the answer to this one's infinity. This one is not infinity. You can use this by summation notation. That's a lot of big words right there. To write a series, for example, the two series above can be written in summation notation. So here's summation notation. Okay, this is a Greek letter, and it actually is sigma. It's the capital letter sigma. Okay, for those of us that are going to be fraternity people later on in life, that's your Greek letter, that's sigma. You don't care yet, but there it is, okay? In mathematics, that means summation. Whatever we're taking after this thing, we're adding it up, okay? Summation. And they've changed the I's right now, and I need to probably do some research. I forget why they do I's right here. I still use N's. I don't know for sure. I think N's just go with series and I's go with summation, but N goes with sequences. I'll mix this up all the time, guys. N goes with sequences. I goes with a series, I think. But I'm going off memory, and maybe that's just what I think about. I equals 1. Typically, that's your bottom right there. Very seldom do you not start with the first term. Later on, when you get into much Cal 2, somewhere in there, sometimes they don't start with 1, okay? And then the top value, that 4, tells me that there's going to be 4 terms. So I to 4, okay, 1, 2, 3, 4 terms. And then what's after this thing is the formula. And again, it's 2i, okay? 2i. Look at my paper here, right? I is 1, that's your first term. You're going up to the 4th term, and this is your formula to define it, okay? Do they actually set it equal to? Yeah, they don't say this is equal to anything. And this one here, I is 1, that's your first term, it's 2i, but then we're going up to infinity because it's an infinite series, okay? So an infinity. You can use summation notation, all right? Sigma notation, yeah, Greek letter sigma written like that, okay? So here we go, A, B. Write this using summation notation. This is example number 4. Letter A is a 25 plus 50 plus 75 plus ... and then it says 250. Okay, so that's a finite. That's finite. B is 1/2 plus 2/3 plus 3/4 plus 4/5 plus ... That one is infinite. Dang right it is. All right, here we go. Here's my paper. Let me try to straighten that up for you. 25. So the first term is 25. The second term is 50. The third term is 75. ... I don't know what this one is 250. Okay. Well, of course, they make the examples pretty easy for you. 1/4, 2/4, 3/4. This will be 10/4. So we're going to write this summation notation. Okay. That's the Greek letter sigma. I equals 1. Typically, that's what we'll have. And it looks like we should go up to the 10 of these because there's 10 values. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 to get to 250. And the way we're going to get this is just what? N times 25, I think. 2, 3, yeah. So that one's fairly easy. Sorry, I look at myself over here when I do that. I need to look at this. I look at this, but now I can't see you. It's weird. But it probably looks better if I look into the camera. You theater people know all about that stuff. Letter B. First term is 1/2. Second term is 2/3. Third term is 3/4. Sometimes you don't need to do this over here. You can probably see it. This is the first term. That's the second term, third term, fourth term. It's going on to infinity. First term, second term, third term. Sometimes it's easier to put it right there than to make a list. Whatever you got to do, guys. Summation notation. I equals 1. We're going to go to infinity because it's infinite series. 1, 2, 3, 4. So this is just an n. And this is 2, 3, 4, 5. So this is just n plus 1. And so that one's pretty easy. Okay, some of these, again, are pretty darn easy. Some of them aren't as easy. Here's the answer that they have in the book. Here's the answer that they have in the book. So write these using summation notation. Here's an infinite series in a one of these. I don't know. Somebody always wants us to do the hard one. I won't mention any names. I don't. It's funny how the hard ones can sometimes be easy and the easy ones are sometimes hard. It's just whatever you see it. 5, 6, 7, ... 12. I think this one's going to be fairly easy. And these are plus, so these are a series, okay? These are series. First term is a 5, second term is a 6, third term is a 7. Plus 4, plus 4, plus 4. I equals 1. I did it. I plus 4. Now, how many times do I have to get to 12? 12 minus 4. 8, 9, 10, 11, 12. So we got to go 8. First term, second term, third term. We got to get all the way to 8 to get to 12. Okay? Now, you don't have to find out what the value is or anything like that. We just have to write it. Write it using notation. And at some point, you may have to find out what these values are. We're leading that into too fast. Okay. Oh, here it is. Find the sum. And I don't know if you have to do this on your homework or not. Later on, you're going to find out there's kind of a cheat way to do this. Right now, you just use your calculator. So this one here, guys, this one here doesn't start at 1. This one starts at 4. So we're just plugging in, and they use K this time. I guess, I don't know why they use K this time. I don't know. Be sure to use upper and lower cases, summation, some series, whatever. The index summation does not have to be an I. Any letter can be used. Again, that's why I think I've seen an N a lot of times. So we're just going to do 4 squared. So we get 19. We'll get 28, 39, 52, and we'll just add those up. Use your calculator and add them up. You get it real quick. For series with many terms, you can find the sum by adding the terms it can be tedious. This can be tedious by adding these up. Below are some formulas you can use to find the sum of 3 special type series. I'm not sure I like this that much, but it can help you some, right? Sum of n series of 1. I don't know. Sum of the first n positive integers. Sum of the squares of the first positives. I don't ever remember doing this. This is all new stuff to me. 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, 6 squared, 7 squared. It's probably just easier to add 1 squared plus 2 squared plus 3 squared plus 4 squared plus 5 squared plus 7 squared. But apparently if you use this formula here, you'll get 140 a little bit easier than you would if you just added 1 squared plus 4 plus 9 plus 16 plus 25 plus all the way up to 49. I don't know. And to memorize this formula is impossible. So, of course, we would give you this part. Okay. I don't remember doing this. I don't remember this at all. I remember summation and series and formulas, but I don't remember these formulas. Find the sum of these series. Let's just pick one right here. Well, this one's easy. Because it's just 1. You plug in a 1, you get 1. Plug in a 2, you get 1. Plug in a 3, you get a 1. Plug in a 4, you get a 1. Plug in a 5, you get a 1. So you're doing 1 plus 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 1 all the way up to 34. I think you can get 34. That's why this one says this. It's just going to be equal to n, 34. If I plug in 1, I'll get 1. If I plug in 2, I'll get 2. If I plug in 3, I'll get 3. 4, I'll get 4. 5, I'll get 5. 6, I'll get 6. Add them up. But you can use this formula right here if you want, just because it's an I. This is k squared minus 1. That's it. We got our exercises. I've talked long enough, guys. I've taken a lot of your time. I apologize for this. You know that there's a little setting on this YouTube that you can speed this up and make it talk a little bit faster than just the one speed. Sometimes you can speed this up to 1.25 or 1.5 or 1.75, sometimes even twice as fast. And it goes pretty well, and that helps you guys out. So here's your formula, or here's your problems here. Okay, I'm going to add this whole section like I've always done. I'm going to add this, of course, this video, and then I'm going to put your problems down in the. You got 11 problems. 11 problems. Due Tuesday. Due Tuesday. I'll have office hours on Friday. So office hours on Friday, I'll make some time just for you guys. That's where you guys can ask your questions, okay? But you can ask any questions, of course, over this lesson or anything previous, and be happy to ask and answer away. I'll probably set that up. I'll make that sometime tomorrow. I'll run office hours tomorrow, too, for you guys. But I'll run them twice. I'll run them tomorrow for you guys, and I'll run them Friday for you guys. I can run them Monday, too. If you ever run across something, I've had this already. I've had 2 students actually email me and say, man, I need some help. Man, it doesn't matter what time it is. I know it's after 5 o'clock. I don't care. What else am I doing? I'll set up a Google Meet, or you can set up a Google Meet, I think even. But whatever you want, just check with me via email or remind text message. I typically carry my phone around with me all the time. I got it right now with me, except it's dead. So it doesn't help me. But I got emails or whatever. I get reminded on my computer. Just let me know if you ever need something, guys. I'm still here for you guys. So got your problems for you. There they are real quick, and I'll put them in the description. You probably can't read my writing right there. It looks like it's a lot. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 questions. Okay, 11 questions. Not bad. And then on Tuesday, I'll have them worked out for you. But let's get this in by Tuesday morning. Okay, get it in by Tuesday morning. So you guys are falling a little bit behind. Let's get back on task right now. I've kind of gotten a little rut myself. I'm almost tired of doing this, but we're back into a good swing of actual lessons and getting you what you need for your topic. All right, guys. Let me know if you need something, please. I miss y'all. I'm done. Coach Mayer out.